Hi, welcome to this e-lecture on multi-threaded programming. In this e-lecture, we're going to be learning the various aspects of multi-threaded programming, as well as data protection, as well as synchronization techniques that we can use while we are running our application on the OS. In multi-threaded design, basically each thread is implemented, okay, as a sort of a function, okay, that has some initialization, okay, where you sort of define and set some initial parameters and settings. And once you do that, you actually enter an infinite loop, okay, infinite processing loop, okay. And this loop basically is designed such that it should run, okay, indefinitely. But of course, uh, we will put in mechanisms in place to ensure that uh, the thread also allows other threads CPU time, okay, to process. So we will be exploring how this can be done, okay. So usually when we say infinite loop in a single threaded context, you will uh, take it to be that it is stuck there forever. But in a multi-threaded context, it is an infinite loop, but yet you are able to give up the CPU to allow another thread to take over and run at specific times, okay. And usually what happens is you design a thread such that you wait for some data or wait for some event, okay. And when that event or data comes through, then you allow yourself to process it, okay. And once you are done, you can go back to the top of the loop, okay, and then wait for the next set of data or events to occur, okay. And all this is done by making calls to runtime routines, which is basically known as the kernel of the OS, okay. And the kernel of the OS is basically the heart of it, and it manages all the OS resources, and it provides us with the mechanisms, okay, to do the switching from one task to another task, as well as all the other sort of very nice and amazing features such as coordination, synchronization, and communications, okay, which we'll be exploring in this lecture. So each thread runs as if it owns the CPU to itself, okay. But of course, there will always be uh, a lot of interaction between one thread and another thread, okay. So we will also have to manage that as well. And what we need to do is now we need to sort of have a change in the mindset. So this is quite an important thing. We need to partition the background into a set of independent threads, okay. And so the total program complexity sort of becomes a lot easier to manage, okay. So this requires a mindset change from our typical single-threaded approach that we have been used to thinking, okay. So that is sort of the key change that we need to adapt, okay, when we move towards the OS. And the idea of concurrency in a OS based system is that uh, you have multiple threads, but only one thread runs at a time, okay, while the others are in a what you call suspended state. Okay, suspended is a general term. It could be in a block state. It could also be in a ready state, okay, depending on whether resources are available or not available at that time. Yeah, and the processor will actually switch between one thread to another, okay, one thread to another very quickly, okay. And it happens so fast in the background that it seems as if everything is running concurrently, okay. So that is why we sort of say that in OS multiple threads run in concurrency. The programmer has a big responsibility in assigning priority, okay. Why? Because this priority that we assign to each thread will sort of set in place how the different threads will sort of uh, use the CPU over time, okay. So that leads us to another important aspect of the OS, which is the scheduler, which whose main task is to determine which thread I should run next, okay, in the system. So this is an example of for example a remote control car here, okay. So for example RC car that you're going to uh, design and develop, okay. So if you think of this as a car, okay, uh, or an autonomous car, basically what will you do in a single threaded context? In a single threaded context, you will have initialization, okay. After that, you will probably have an infinite loop where you will say that I run the motors and then I check for my sensor over here to detect some obstacles, okay. If I detect some obstacles, then I have some if-else statements to decide whether I should turn right or turn left and so on, and then I sort of repeat this indefinitely. Okay, so this is how we will typically run it in a single threaded context. Okay, but in a OS, okay, so in the OS context, okay, what we need to do is we now need to break up this objective of operating this autonomous vehicle into multiple tasks. Okay, so we can say that one task is a task motor to manage the movement of the motors, one is for task sensor to manage the sensor reading, and the other is for the main task, okay, that will manage both the motor and the sensor. Okay, and in this case here, example, you can see that I've assigned a priority level of 2 to task main, and 3 to task motor, and 4 to task sensor. So in this example, task main has the highest priority, followed by task motor with a medium priority, and task sensor with a low priority. And how I would design something like this would be, for example, once the main task starts to run, okay, I probably do some initialization of the system, and once that is done, I sort of put myself into a block mode so that I allow the next higher priority task to run. So when that happens, when I put myself into a block state, okay, the OS will allow the next higher priority task to run, which in this case task motor, and task motor will run. Okay, and while it is running, okay, I can decide how I want to manage the task sensor. In this case, I may use a yield, which is to voluntarily give up the CPU so that I allow the next available task, which is task sensor, to run. Okay, and when the task sensor is running, it can also monitor the sensor information, and if needed, send data back to the task motor to make the motor stop moving. Okay, if not, the motor can carry on moving. So this is sort of just a high level idea on how you actually break up a high level objective into multiple tasks that you can run on your OS based system. Okay, within thread, okay, we say that a thread has its own stack, okay, and a special region of memory known as context. Okay, because you are continuously switching between one thread or to another thread, you need to always be able to keep a context. That means, for example, thread A or task A, when it was running, at which line was my program counter, what are all the values in the registers, okay, how was my stack, all this information needs to be captured, okay, within its own context before I can switch to another task, okay, and get the other task to run. Okay, and that is basically what we call context switching. Okay, and this happens very regularly, okay, in most OS based systems, and it happens very fast. Okay, so even though it seems that everything is concurrent, but in reality there is a lot of context switching happening in the background. Okay, so for example, if I'm currently in thread A, okay, and I'm going to do a switch to thread B, then at that point of time when I'm going to switch over, I need to save the context of task A and restore the context of task B. Okay, then I can switch over. And similarly, when I want to switch back, I save the context of task B and restore the context of task A. Okay, the good part is all of this is actually done transparently, okay, to the programmer, because the OS handles it. Okay, so as far as the programmer is concerned, this is done and managed by the OS in the background. Okay, but we need to, of course, have certain rules in place on how we design the OS code and how we assign priorities and so on, so that we actually are making full use of the OS to fulfill our objectives. Now, in terms of multitasking, there are two approaches. One is preemptive, the other is non-preemptive. In a non-preemptive context, basically what happens is the process that is currently running needs to call a yield function. When you say yield, means you are basically voluntarily giving up the CPU. Okay, and that is basically also known as cooperative multitasking. So most OS systems that do not have any strict timing deadlines to meet. For example, your general purpose computers that run on OS or Linux and so on. They are, in a sense, OS based systems without any strict timing deadlines or constraints. And so we call them cooperative multitasking systems. Okay, so they allow tasks to voluntarily give up themselves so that another task can take over the CPU and run. Okay, the issue with non-preemptive multitasking system is when I call yield, okay, there can be a lot of threads that are in the queue waiting to run. Okay, so you cannot effectively say for sure that so for example, if I have task 1, task 2, task 3, task 4 and so on, okay, and if task 2 is currently running, okay, if task 2 is currently running and at this point of time there is some data that task 3 needs, okay, so when task 2 is running, okay, at this point of time there is some data, okay, and task 3 needs this data, okay, but when T2 calls the yield function, okay, at this point of time, where will I switch to? Okay, where will the OS switch to? Will I switch to task 1 or task 3 or task 4? It's a bit difficult to say because we need to look at the structure of how the OS determines, okay, the next task, and in most cases it will probably choose the task with the highest priority. Okay, so if the system is designed that way, then even though the data came in for task 3, but if task 1 is higher priority, then maybe I will switch to task 1. Okay, so there is a bit of a difficulty in ensuring that the task that you want to run at a particular time will actually be able to run, even though the current task is already called yield. Okay, so the real-time nature is not predictable. Okay, so that is the example here. Okay, so when I call yield, okay, the scheduler will select the highest priority thread, okay, that is currently ready to run. Okay, so which means that I cannot guarantee that the thread that I want to run will actually run. Okay, because it depends on the priority of the threads waiting in the queue. So of course, in order to fulfill systems that have very strict timing constraints, such an approach that we saw earlier is not practical. Okay, so the whole idea is you want to switch to a preemptive multitasking system. In a preemptive system, basically the highest priority task, okay, that becomes ready, okay, can trigger a context switch. Okay, so when I have a task that is running, okay, and task 2 is running and task 1 is in a block state. Okay, so when task 2, which is medium priority, and task 1, which is high priority, okay, so initially let's say task 1 is blocked, okay, and task 2 is running. Okay, at the point of time when task 1 becomes ready, then I can immediately trigger a context switch over to task 1. Okay, so automatically the OS will allow the highest priority task that is ready to take over the CPU. Okay, so that is the true nature of a real-time system. Okay, because when you assign a task a high priority, that means the moment it is ready to run, it should be given the CPU so that it can execute. Okay, there are also ways in which the interrupt, okay, can trigger a context switch. Okay, so I think that is a bit clearer here as well. Okay, so for example here, task A is running which is lower priority, and I have task B, okay, which is higher priority. Okay, so when task B is blocked and then it suddenly becomes ready, so when will I transit from blocked to ready? So in this case, okay, which we'll be covering in a while, in most cases when you say you're blocked means you are waiting for some resource. Okay, so you're waiting for some resource that is not available yet. Okay, and in this scenario, one possible event that can happen is an ISR could be triggered. So interrupt service routine, as you've seen before, again is separate from your main code. It can trigger anytime, but once it is triggered, you will jump to an interrupt service routine. And when I jump to interrupt service routine, I may run some code and I may release this resource, okay, that task B was waiting for. So once that resource is released, the OS will change the task B from block state to ready state. And once task B, which is higher priority, changes to ready state, the OS will cause a context switch to happen. Okay, that means task A will become ready, and I will switch over to task B to allow task B to run. Okay, so that is what we call a preemptive kernel, okay, in a real-time system. Okay, so that is again explained a bit neatly here as well. Okay, where you have a thread that is executing. Okay, and when the ISR comes in, it releases some resource that triggers a context switch to happen. Okay, so in a sense, when I return from the ISR, I actually do not go back to thread A, I actually go to thread B. Okay, now so that is the general idea of multi-threaded sort of design in terms of context switching between two different tasks. Now as you can see, the context switches happen or can happen at any time, okay, because it's all very dynamic, depends on whichever task is holding on to resources, which other tasks release resources, okay, and how we design the priorities of the system and so on. Now so that leads us to a very important aspect of data protection, okay, where we need to ensure two things. One is the data integrity must always be there. The other thing is what we call a critical section of a code. Okay, so a critical section of a code where proper execution, okay, is based on the assumption that you have exclusive access to the shared resources, okay, during the execution of a sequence. Okay, so a critical section is once I enter a critical section, I must be able to finish the entire section without being preempted. Okay, and even if I happen to be preempted, all the resources, okay, the shared resources that I am having access to must still be locked in by this particular task here. Okay, let's say I call it task A. Okay, and why is this important? Because in many of our code bases, we may have shared memory elements. Okay, so you may have a shared buffer that both task A will access and both task B will access. Okay, so if both of them are reading and writing to this shared memory, okay, if we want to ensure data integrity, we need to make sure that if task A is doing something to this shared memory, it must be allowed to complete fully before task B has any access to it. So that is what we call a critical section. Okay, and atomic operations are basically operations that can execute to completion without preemption. Okay, so when I say that a particular operation is atomic, that means once this operation is started, I will ensure that it will still complete even if there is preemption. Okay, so this is an example of shared data between two processors. So for example, in your handphone camera usage, okay, you may have a task that is designed to just capture the raw image and put it into a shared buffer, and subsequently you can have another task that takes charge of compressing this raw image to a different format like the JPEG format and so on for more optimum space usage. So in this kind of situation, we may be taking multiple pictures, okay, and for each picture we also need to call the T compression task to go and compress it. Okay, and both of them could be accessing the same sort of memory region. So we want to make sure that if T camera is updating a particular memory region, T compression should not be trying to access it at a time, okay, until it is complete. Okay, so that is an example of a shared memory access. Okay, so how can I protect data, okay, or protect this critical section? Okay, so one way is I can disable interrupts, okay, because as we know, when a task is running, okay, any point of time I may still go to interrupt, and the interrupt and the task may also both try to access a shared memory region. Okay, so if a task and interrupt are both having access to a shared memory region, then I can disable interrupts. Okay, or have a way of making sure I have exclusive access, okay, to shared resources. Okay. Uh, so shared resources, okay, so in multi-threaded application, okay, we usually can pass information from one task to another task to a common data structure, okay, and one of the most popular one is of course a shared memory. Okay, so I just declare a shared memory that is globally accessible by multiple tasks. So to protect this shared memory, okay, like as we have seen before, one thing is you have an issue of a thread and an ISR, okay, or two ISRs, okay. So within a thread and ISR, I can say I disable the interrupt, okay. So I can say disable interrupt to protect, okay. Between two ISR, that means you have a one ISR being preempted by another ISR. So I can say I disable nested interrupts. Okay, I disable nested interrupt, so only one interrupt can happen at a time. The issue that we are more concerned with is this between two threads, okay, because in the OS context, this is the scenario that most often occurs. Okay, so again, this is an example of what you mean by uncontrolled access to a shared resource. So this is how a typical code with a shared uh, resource looks like. So in this case, both of them, okay, task 1 and task 2, both of them are calling this function, which is basically going to modify a variable, okay, in this case k. In this case, a global variable. Okay, that means both of them can access this variable concurrently, okay, in essence. So even though we write this k equals to k plus 1 as a single line in your C program, we know from how a processor architecture behaves, this k equals k plus 1 is actually multiple instructions at the lower assembly level. Okay, so in order for me to actually execute this code, I need to first load this memory location k, okay, the data that is already in k in the memory, load it, okay, to a register. So from memory I need to move it to a register, then I increment the value in the register, and finally I write it back to memory. Okay, because k is actually a variable, that means it is a memory element, okay, it's inside our storage. So we need to do these 3 steps to complete this single one line instruction in C. Okay, and that means that I can actually get preempted anytime, okay, within these 3 lines. So in a single threaded context, basically this is what will happen, correct? I will load the current value, okay, increment the value, and then store it back, okay, and everything works fine. But in a multi-threaded context, what can happen? Okay, so you can see that a few things can happen. So for example, I read the current value of k, I increment it, but before I can write it back, okay, so this is the case of the expected result. Okay, that means everything goes on smoothly. So if everything goes on smoothly, task 1 reads, increments, and writes it back. Then task 2 reads, increments, and writes it back. Okay, but what if a context switch happens in between? So task 1 reads, increments it, but before it writes back, there's a context switch. That means I switch over to task 2, and task 2 does a read. Okay, so you can see that even though task 1 has actually incremented it, but it did not write back. So since it did not write back and the context switch has happened, when task 2 runs, it will still load the original value that is still in the memory. Okay, so you can see that in this case, okay, the change in k will only be from 0 to 1 instead of 0 to 2. Okay, even though two tasks were both trying to increment k. Okay, and the issue with this is because the nature of real-time systems is very dynamic, you may not see this incorrect result all the time. Okay, so sometimes it may seem correct, sometimes it may seem incorrect. Okay, and that is the tricky part. Okay, so we need to be very careful, okay, in making sure that shared data are always protected, okay, to ensure that data integrity is there. Okay, so as we have seen before, how we can protect, we can disable interrupts. Okay, that is one option. The option that is more important for us is this idea called Mutex, which basically stands for mutual exclusion. And the whole idea of mutual exclusion is you take a mutex, okay, or pen, and you do this before you enter the critical section, and once you finish with the critical section and you're going to exit, then you post it or you give it back. Okay, and that means that at any point of time only a single thread is allowed to hold on to the mutex, and once you lock the mutex, another task that tries to lock the mutex will not be able to lock it. That means the other task will not be able to proceed with accessing the shared resource. So this is an example of how we can use it. Okay, so for example, in task A, when it's running and I want to access, so this is the region, this is the critical section. Okay, and in this critical section, before I access it, I lock it, and after I finish, I unlock it. Okay, I lock and unlock, and that means that if in between, okay, after I lock it, I get context switch out to task B. Okay, and if task B also tries to access the shared resource, it must do a mutex lock. And what will happen? The OS will say that somebody else has already locked the mutex, which is task A. Okay, and since somebody else has already locked the mutex, it will cause the current task to go to a block state until the mutex is freed up. So until task A finishes his access and unlocks the mutex, then I can have a context switch over to task B. Okay, and task B can carry on from there. Okay, so that is the whole idea of mutex. Okay, now the whole idea of all these OS mechanisms, uh, though they are there, it is still the programmer's responsibility to ensure that the rules are being followed during implementation. Okay, so what do I mean? If task A follows the rules and task A says, okay, this is the shared resource, and whenever I want to share, I want to access the shared resource, I must lock and I must unlock. Okay, so after I finish, I must say unlock. Okay, but task B, okay, also is using the same shared resource, but task B does not follow the rules, and when task B gets a chance to run, it goes ahead to access the shared data without doing any lock and unlock of the mutex. So in this case, task B will still be able to corrupt the data. Okay, so even though task A has acquired the mutex, okay, task B will still be able to corrupt the data. Okay, so this is an important concept to understand. The idea that the mutex is linked to a shared resource, is shared to some important functions and data access. This idea is only within the programmer's mind. Only the programmer knows why this mutex is there. What am I trying to protect? Okay, so that means every task that is going to access this shared resource, shared data, must follow the rules. Okay, if a task, especially in a big project, maybe you have across multiple teams, okay, and there's shared data and resources that are across these teams. It is quite common that maybe one or two of these software developers may have forgotten that this is a shared resource and we need to protect it. Okay, and in that case, when they try to access this shared data without the proper locking mechanism, they will still access it, even though it may have been locked by a previous task. Okay, and that is where all the issues start to come up, and then you have to troubleshoot and figure out who didn't follow the rules. Okay, so this is again the idea. Before the critical section, you take the mutex, and after that you give it back. Okay, so this is basically how the code would have been improved, okay, to ensure that you do not have any issues with concurrency, okay, with both tasks accessing a shared resource. Now another important construct in our OS is what we call semaphores. Okay, but it's used to manage events. Okay, more so than being a shared resource. Okay, and it also provides a signaling mechanism. So I can have one task signaling to another task that I have already accomplished certain aspects. Okay, then another task can take over and so on. Okay, so it actually can work as a sort of communication link, but you're not sending data, but you're sort of synchronizing between when one task should run, when another task should wait, and so on. And semaphores contain what we call a count. Okay, and this count is incremented by the producer and decremented by the consumer. Okay, so this producer consumer is a general term. Basically what we need to do is we need to first have a semaphore, okay, with the number of resources that we have. Okay, and the count, okay, cannot go below 0 and cannot go above n, which is the number of resources. Okay, and every time I take, I have to reduce the number. Every time I give, I increase the number. Okay, and of course you cannot go beyond the limits. That means I cannot go below 0, I cannot go above n. Okay? And one of the primitives for semaphore is this OSM pen and OSM post. Okay, basically what you need to do is, again, when I take a semaphore, I check the value, and if it is greater than 0, then I can decrement by 1 and return. If not, what happens? I block the process. Okay, so it's similar to the mutex just now. Okay, as we saw earlier, if a task tries to lock the mutex and is not able to lock the mutex, then it goes to a block state. Similarly, when a task tries to take a semaphore but is unable to take it, it will also go to a block state. Okay, and on the other side, you have the semaphores, which is for a task to post a semaphore. Okay, and when you post a semaphore, you're going to increment the count by 1. Okay, so this is an example here. So for example, in this situation, we have 3 resources. So the task first takes 1, okay, then the count reduces, takes another 1, okay, and then it increments, okay, it gives back. Okay, so P is to take, B is to give. So I give back, though the count increments. Okay, subsequently I take again, so it decreases. I take one more time, then it decreases all the way to 0. Now once the resource count is 0, which means that you have no more resources. So when a task tries to take the semaphore at this time, what will happen? It will get blocked. Okay, similarly process Y will get blocked again because it also tries to take when there's no more resources available. Okay, until somebody releases the resource. When somebody releases the resource, then the task that was waiting for it will get it. Okay, similarly again, when I release again, since another task is also in the queue waiting for it, then I will unblock the process and give it to that process. Okay, finally, when I give back and there's no task waiting for it, then the count will go up by 1. Yes, so this is also another idea, same idea, with the explanation of how things work. So you can see here that my initial semaphore count is 0. So when my semaphore count is 0 means there are no more resources available. Okay, and when a task tries to take a semaphore, it will cause the current thread to be blocked because I have 0 semaphore, which means that no resources to actually allocate to the task. So in this situation, I will get blocked until somebody posts a semaphore. So who can post a semaphore? Anybody. Okay, another task, another ISR, anyone can post a semaphore. And when they post a semaphore, what happens? The OS will see that there is actually a task that is in the block state waiting for the semaphore. Okay, and it will cause it will allocate the semaphore to that task and cause it to become unblocked. Okay, so that is basically the idea of a semaphore. And you can also achieve a similar application with Mutex, okay, as well as Semaphore. Basically, if I declare if I initialize my Semaphore with a value of 1, then it actually is known as a binary Semaphore. And in this situation, it actually behaves the same as a Mutex. Okay, now let's look at communication through message passing. So communication, as you have seen, as I've discussed before, tasks, even though they are designed to run as if they own the CPU by itself and they are in essence independent, but actually in a real system, the tasks all need to communicate with each other, need to send information to each other. Okay, and we have already seen one way in which that can happen, which is a shared data, a shared buffer, a shared resource, memory resource, where one task can write to it, another task can read from it. Okay, that is a normal memory allocation approach that we are used to. Another common way of communicating between tasks is through what we call message passing. Okay, and this is a mechanism built in to the OS itself. Okay, so it is a high level interprocess communication. Okay, and all OSs support some form of message passing technique. And basically what you need to do is you have two primitives. One is send, one is receive. Okay, and send allows you to send a message to another process, while receive allows a process to block waiting for a message. Okay, so this actually implies synchronization. Okay, that means if a task calls to receive function and nobody has actually sent any message, then it will get blocked. Okay, it will get blocked until somebody sends a message. Okay, so this is an example, okay, where the receiver calls first, okay, but then there is nobody to send. Okay, the send comes later. So when the send comes later, then the task B will wake up and then proceed from that. So in a message queue, this is typically what happens. In this case, task A is writing to the queue and task B is reading from the queue. So whenever it sends, it pushes it to the queue, and subsequently task B can read from the queue. Okay, so every time it reads one copy and then the data shifts back up again. So in message passing, basically what you're doing is you're doing a message copy. Okay, so if task A writes to a message queue, okay, in this case task A this task writing to a message queue here, it is actually a copy. Right, it's a copy. So the original data is still here, and after I send the original data, if I change it, it does not affect the data that's been sent. Okay, because it's like a copy paste. Okay, so once I do a copy paste, similarly the receiving task will also take a copy from the message queue and bring it over to the task internal memory. So there are two types of naming mechanisms. One is called direct, the other is called indirect. Indirect, basically you know exactly who you're sending to, so I can actually send from one task to another task directly, or in indirect I can actually send to a generic mailbox and I can receive from this generic mailbox. Okay, so these are the two schemes here. So in direct, you can see that one task, in this case task P, can directly send to task Q. Okay, but in indirect naming mechanisms, I will write to a generic mailbox. Okay, and this mailbox can be accessed by multiple tasks. Okay, so everybody can read from this mailbox. Okay, so in both these cases, we support one-to-one and many-to-one. Okay, and in indirect, you also support one-to-many and many-to-many. Okay, because many people or many tasks can write to a common mailbox, and again, many other tasks can also read from this common mailbox. Okay, in terms of receiving, okay, we saw just now that there is a blocking receive. That means the receiver must wait for a message if nobody has sent it yet. There is also a non-blocking receive. Okay, if in a non-blocking receive context, when the message comes in, when the receiver calls for a message receive function, but nobody has sent it any message, it can still proceed on. Okay, and carry on doing other things. Okay, but as you can see, the most common one is actually the blocking, because you want to ensure that the message is having some important data that I want to receive before I proceed on to doing the next step. In asynchronous, in message passing, we say that the sender is never blocked, okay, because even if nobody calls to receive, the sender can still send, okay. But of course, the sender has to understand that there is always a finite buffer size, okay, in the message. So that means uh, when you reach that full buffer size, then you may be blocked until further blocked from sending further messages until the queue is cleared up. So in this, you see the asynchronous message passing, where the receiver calls it first, okay, and in this case the receiver is blocked until the sender sends. In this scenario here, the sender sends and then he carries on, and then the task B later on calls to receive and immediately gets the data. Okay, so the message buffers, okay, basically need to be designed to be large enough to handle the data that we are going to send through these buffers. Okay, in synchronous message passing, the sender can also be blocked. Okay, so after I send, I can be blocked until the receiver performs matching receive. Okay, so this is of course one way of preventing any buffer overflow, because after the sender sends, it cannot carry on and keep sending data unless somebody actually reading the data. Okay, so in this case, you don't need any buffering issue. You don't have any buffering issue, because when the sender sends, the receiver must receive before the sender can carry on again. Okay, so in this example, you can see that the sender sends first, but nobody receives, so I have to be blocked. Okay, so in this case, I am blocked here until the receiver calls a receive function and the message is cleared. Okay, so now let's look at the Macro-C OS 3 code that we are actually going to be using for our assignment, as well as for improving our understanding. Basically, in OS code, we call the OS init function first, okay, to initialize the Macro-C OS. And after that, we can call the OS start, which is to start the multitasking. So once you call OS start, you are switching from the single threaded mode to multi-threaded mode. Okay, and in the multi-threaded mode, what you can do is then you can start to create tasks. Okay, so when you create tasks, okay, so you see a lot of parameters here. You do not need to be overly concerned. Okay, when you look at the sample code, you just copy from the sample code and then you make the changes for the relevant parts, which are basically the names, the priority, and so on. Okay, and each task is written, okay, like this. Okay, as you can see, it is effectively a while one loop. Okay, and before this while one loop, there is already some initialization done here. Okay, so initialization, and subsequently it is a while one loop, and within the while one loop, you must have some calls to OS kernel that can potentially cause a context switch. Okay, if you do not have any calls that can cause a context switch, then potentially this task, if it is a high priority task, it may just hog the CPU, okay, and preventing any other task from running. Okay, how can I give up the CPU voluntarily? Okay, that is by calling OS task suspend. Okay, so by calling OS task suspend, I suspend the current task, so it does not come into the scheduler queue, and then I resume. Okay, I'll put myself back into the queue by calling OS task resume. Okay, just now we talked about semaphore. So the way I can create semaphore is called OSM create. Okay, when you call OSM create, you again provide some parameters and you provide the initial count value to know what is the initial count of the semaphore. To take the semaphore is OSM pen, as we have discussed, and OS sem post is to give the semaphore. There is also a OS time delay function. This is in terms of ticks, which can be a bit difficult to handle sometimes, okay, unless you really know how many what is the duration of each tick within the system. Another more common delay is this OS time delay HMSM, which is basically to delay in terms of hours, minutes, seconds, and milliseconds. So this provides a bit more of an easier way to call delay. So when you call OS time delay, you're actually giving up the CPU, okay, in this current task to allow another task to take over and run. Okay, so let's look at the demo code for the semaphore usage. So in the demo code, basically you can see that I create a task and I create a semaphore. And once I start the OS, which is in here, OS start. Once this is executed, I will run my start task. So you can see the start task is the first task that I created. So once I call OS start, I will run start task. And in start task, what will happen? I will create two other tasks, send A and send B. And after I create two other tasks, I go and suspend my task indefinitely. Okay, so I suspend my task indefinitely. And what happens is I have task A and task B. And in send A task, what do? I take a semaphore, I print hello, and then I post a semaphore. Okay, and then I call delay. So if I look at the timeline over here, what's happening? Task A runs first. Okay, so of course what is not shown is actually task A is higher priority than task B, so that's why task A will run first. So when task A runs, it takes the semaphore, it prints hello, then it posts the semaphore, and then it calls time delay. After it calls OS time delay for 500 milliseconds, then what happens is it actually goes into a block state for that duration of time. And in the duration of time, once you go to a block state, the OS will see what are the other tasks in the system. Okay, and you will see that I have a task B. So when I have a task B, and task A has gone to a block state, so I will do a context switch from task A to task B. So task B will start to run. It will also do the same thing. It will take the semaphore, print out world, post the semaphore, and then delay. Okay, and after that it will also call. So when it calls delay, again it is going to delay itself. Now the important thing here is just because task B calls delay doesn't mean I go to a context switch yet, because this code here will execute very fast compared to the delay of 500 milliseconds that task A is currently in, which means that after task B completes this code and calls delay 500, it will go to a block state and task A is still in the block state. Okay, so there will be a period of time where both the task A and task B are in the block state, but because task A called the delay first, it will come out of the delay first. Okay, so task A will eventually resume and then it will go through the whole process again. Similarly, task B will also come out, but it cannot resume yet because at that point of time, maybe task A is running. Okay. Now let's look at message queues in Micro:C OS 3. In message queues, basically you can post messages to a queue and you can read. So the whole idea is you first create a message queue and then you can post from it and you can read from it. Okay. So that is the whole idea over here. Okay. So a task or ISR, both of them can post messages to a message queue, and a task can also read from it. Okay. As you can see here, the default is first in, first out. That means the first message to go in is the first message to come out. Okay, but you can also do a LIFO order if you want. Okay, but most of the time we have a default, which is the FIFO order. Okay. So in the message queue, okay, you also have a list of tasks waiting for messages to be sent to the message queue. Okay, so multiple tasks can wait on a message queue. Okay, and when a message is sent to the message queue, the highest priority task waiting on a message queue will receive the message. Okay, that means there can be multiple tasks that are sending to the message queue. Okay, and if assuming that before anybody send, many tasks have already tried to read from it. Okay, many tasks have already tried to read from it. Okay, and in that situation, okay, when a message is sent to the message queue, the highest priority task waiting on the message queue receive the message. Okay, so if there are multiple tasks waiting, whoever is the highest priority will get that message. Okay, so that is the message queue idea in OS3. Okay, so there are multiple tasks here, as you can see. Okay, and each of them are waiting. Okay, so when somebody eventually posts a message, then the highest priority task gets it. There is also an idea called task message queue. So this is a generic message queue. Okay, so if you look at all uh, the OS construct is called OS queue here. Okay, there's also another kind of message known as the task queue. So as you see here, it's called OS task queue everywhere. So in OS task queue, it is actually a direct message passing context. Okay, if you recall just now in message passing, we talked about direct and indirect naming mechanism. So this generic queue here is indirect because anybody can post to this generic message queue, anybody can read from it. But this task message queue is very direct. That means one task specifically sending to another task. Okay, so that is why it's called a direct message queue. Okay, so you do not need to create any separate message queue. You can use this inbuilt task message queue. Okay, so this is actually quite a nice feature because you do not need to have another message queue and it simplifies your code. Okay, without having to do all this. Okay, let's look at the demo for message queues. So for message queues, you first need to create a message. Okay, so this is the code to create a message. In this case, I create a message with 10 messages. And in this example here, what I do is I first post. Okay, I first post, okay, count value to my message queue. So inside my message queue, okay, I put in a value here. I post a message here. Okay, and after that, what do? I do a sempan. Okay, I do a sempan because I want to wait for the message to be read and I want to get a notification that the message has been read. Okay, so what I'm going to do is I do a sempan, okay, to see if the message has been already read, okay, from the other task. Okay, so the semaphore is used for synchronization. And after that, what I do another once I get the sempan, then I can do a OSQ pen. That means I want to receive a message. Okay, so in this I do a post and here I do a pen of the queue. Okay, so I post a message to the queue and then I wait for the semaphore and then I do a OSQ pen. Okay, if I do a OS post and OSQ post and pen directly over here, what would happen? I would post and I will get it back immediately because I'm still running. Okay, so that is why I'm using the semaphore to actually put myself into a block state, okay, until the other task has actually received the message and done something about it. Okay, so in the other task, okay, what will happen is I will call OSQ pen, and when I receive the message, I will increment the message and then post it back. So you can see this message data here is the incremented data. Okay, so if I were to draw the timeline or the sequence, basically you see that task A and task B. Okay, and what is happening is task A will run first. You do a queue post. Okay, after you do a queue post, it will still run, and then it will say sempan. Okay, sempan means I want a semaphore. Okay, and what I've done is in this case I've initialized the semaphore. The initial semaphore value is equals to 0. So when I call a sempan, I will go to a block state. Okay, so from here I go to a block state. So since I go to a block state, task B, which was blocked all the while, okay, or ready all the while, okay, so all the while was ready, and then at this point of time I have a context switch, so I can go to the run state. Okay, so when I go to the run state in task B, what do? I receive the message, increment the value, post the message, and post the semaphore. Okay, so I do 4 things. Okay, so I receive, so I do a queue pen, I receive the message, I increment my value, I do a post, and then I do a SEM post. So when I do a SEM post, what happened? The task A, which was blocked, okay, will receive the semaphore, which means that it will now go from block state to a ready state. Okay, and since it goes to ready state and it's higher priority, this is higher priority, this is lower priority, I will then switch to run state. Okay, so I will be able to run, and in the run, what do I do? So I already got the semaphore here. Okay, so in the next step is to get the message in the queue. So as you can see here, I already posted a message in the queue. So the task A will then be able to do a queue pen. So it will not get blocked because somebody already posts. Task B already posted earlier on. Okay, so when task A does the OS queue pen, it will straight away get the message and you're able to carry on. Okay, so that is the sort of idea on how this message queue code works. Okay, so this is using the generic message queue. There's also another concept that we talk about, which is the task queue. Okay, so in a task message queue, okay, you actually use the message queue that is built into the task. Okay, so the important thing is when you call OS task create, there is one parameter here, which is the task queue size, which you need to specify. Okay, which basically tells us how big is the buffer size you're going to have. Now for this task queue size, then what do I do? When I do a task queue post, I post directly to the task that I want. Okay, so in this case, I'm calling this function in task A, okay, and I'm posting a message to task B. Okay, so in previous case, if you see down here, this OSQ post can be called by anybody, and anybody can post to my queue, which is a generic queue. Okay, but in this case, okay, I'm doing a post from task A directly to task B. So nobody else can receive this message, only task B can receive this message. Okay, and what I do over at the other side in task B is I have a OS task queue pen. So I will block my task until somebody actually send me a message into my queue. Okay, so you can see that this sort of actually simplifies things where I do not need to have an additional message queue. Okay, I can use the built-in task queue to fulfill the objective. Okay, so of course, those examples here, the actual demo that we will go through in class will give you a better understanding, but here I just try to give you the code snippet that sort of gives you the main picture of how we used semaphores and message queues in our message passing. So this sort of summarizes the whole lecture slides on RTOS, okay, and multi-threaded programming. And I hope that you have a good understanding of how the OS architecture works and how the constructs like Mutex, Semaphores, and message passing actually play an important role in allowing us to develop a very complex, and reliable RTOS architecture for our project. Thank you.